Okay, let's consider this problem which is related to photoelectric effect. When electromagnetic radiation of wavelength 300 nanometer, okay, 300 nanometer is less than 400 nanometer, so I think it must be ultraviolet rays, falls on the surface of sodium. So it's falling on the metal sodium and it's releasing electrons are emitted when this is the wavelength which falls on the metal. Electrons are released and the kinetic energy of the electrons are is 1.68 into 10 to the power 5 joules per mole. It's not for one, it's for 1 mole of electron. This much is the kinetic energy. So what is the minimum energy needed to remove one electron from sodium? So you need to find out the minimum energy that is needed to remove one electron from sodium. And what is the maximum wavelength that will cause a photon, that will cause a photoelectron to be emitted. And what will be the corresponding maximum wavelength? So according to Einstein's equation, we know that electromagnetic radiations, the energy is emitted or absorbed in the form of photons, and the energy of each photon is proportional to its frequency. In fact, the energy of one photon is equal to the Planck's constant into frequency, and there's a relationship between the frequency, the wavelength, and speed or velocity of the electromagnetic wave. So new frequency is equal to c by lambda. According to Einstein's equation, the energy of the photon can be broken down into two parts. Some energy is used to eject electron from the metal, that we call the work function of the metal, plus the additional whatever energy is left out is used, it comes out as a kinetic energy of the electron. So that means h nu is equal to h nu naught, which will be the minimum frequency required to remove an electron for the metal, plus kinetic energy. Next, if we rearrange the equation, we what is needed? Let's look back at the question once again. What is the minimum energy needed to remove an electron? So this is what we need to calculate, the minimum energy that is needed to remove an electron. In order to know this, let's keep it in on left hand side. So it will be known by subtracting kinetic energy from the total energy that is contained in the photon. So it will be like this. If you want to calculate this one, it will be like subtracting kinetic energy from the total energy of the photon. So how will we write the total energy of the photon? We're not given frequency. What is given is the wavelength. So to convert this frequency in terms of wavelength. So how would that be? It will be the relationship between the frequency, the speed of the radiation, and the wavelength. So instead of keeping the frequency, we're writing we're keeping the h as it is, and we're writing, instead of frequency, we're writing speed of light divided by wavelength that has been used. So let's put the values of whatever constants we have. The value of Planck's constant is 6.626 into 10 to the power minus 34 joules second. The velocity of the light in the vacuum, the value of c is 3 into 10 to the power 8 meter per second. And the wavelength, it's been given 300 nanometer. So convert the nano means 10 to the power minus 9. So 300 multiplied by 10 to the power minus 9 meter, 300 nanometer. Now what we will subtract is the kinetic energy of the electron. But what the question has given is it's 1.68 into 10 to the power 5 joules per mole. So it's a kinetic energy of 1 mole of electrons. It's not the kinetic energy of 1 electron. So what we need to do is we need to divide this by 1 mole of electrons, because this is kinetic energy of 1 mole of electron. So what will the kinetic energy of one electron? We'll divide it by Avogadro number. So what's the Avogadro number? It's 1.68 into 10 to the power 5. That is the kinetic energy of 1 mole of electron. So the energy of kinetic energy of one electron will be this much value divided by mole. And how much is mole? 6.022 into 10 to the power 23. So this is the equation we have. I think if we solve this equation, what we'll get the answer is 3.293 into 10 to the power minus 19 joules. That would be what the minimum energy required to remove an electron from the sodium metal. So we have got the answer of the first part. What is the minimum energy needed to remove one electron from sodium? So this much energy is needed. 3.293 into 10 to the power minus 19 joules after simplification of this. So what remains is the second part. We need to find out what is the maximum wavelength that will cause a photoelectron to be emitted. So this energy is calculated here. From here, you got a frequency. Now this frequency it can be converted. It can be written in terms of velocity of the wave and its wavelength, which will be like c divided by the maximum wavelength. Minimum frequency is corresponding to the maximum wavelength. This is what we need to calculate. So here what we have the Planck's constant, the velocity of the wave, with the velocity of the electromagnetic wave, and in order to know this, we divide the value of this is 3.293 into 10 to the power minus 19 joules. So we'll divide this value h into c divided by this will give our the wavelength. The Planck's constant as it is 6.626 into 10 to the power minus 34 joules second. The velocity of the light will be 3 into 10 to the power 8 meter per second. When simplified, it will become 517 nanometers when you simplify this. And this one corresponds to green light.